Welcome to part 3 of the Atmos tutorial. Now you know how to run the code, you know how to change the input files to run the code the way you want to run it, for the conditions you want to run it for. Now it's time to open up the output files and get our hands on the data so we can find out what happened. So the main output file you're going to want to look at is out. Actually, there's out.out. And what out.out contains is most of the things you'll need to look at a model run. It has the chemistry that the model thinks it had. I'm going to make the font smaller. Apologies if this becomes an eye test for you, but this code does have pretty wide outputs in terms of the number of columns it contains. So it has the molecular species, the reaction list that it has, then it has some information about the size of the vectors it has. This is some information about lightning chemistry. There's a nice paper by Sonny Harman on the importance of this. So I would recommend you turn that on unless you have a very, very specific reason to turn it off. These are the mixing ratios of especially if you're doing anything that's Earth or ancient Earth-like. These are the mixing ratios at the start of the run, at the long-lived species. So everything at the top of this file is going to be before the model runs. So those are your starting point conditions. These are your mixing ratios. Then it shows some information on the wavelength grid, the photolysis rate. So this is the rates of each photolysis reaction as a function of altitude. And again, this is still at model initiation. These are starting point conditions. Then it gets into the time stepper, which I described before. This tells you which time step you're at, this is saying that the relative change of the least stable molecule. It tells you what that least stable molecule is, at which stable it is the least stable molecule, the concentration of that species at that layer, and the predicted change in that concentration for the next time step. This is then the resulting predicted next time step and the total model runtime. Then it shows you the energy fluxes in watts per meter squared coming in to the top of the atmosphere and reaching the bottom of the atmosphere as a function of wavelength. It can be important for model diagnostics if something funky is happening. And then, and this is, by the way, at the end of here, this is now the end of the time stepper. So now the code has converged. And things like energy fluxes and photolysis rates that we're showing now, this is now at the end of the model run. So I showed you photolysis rates up here. The difference between this printout, I'm going back, how far? This printout here, photolysis rates, and the one after the time, I'm going down now, and the one after the time stepper is the first one was before the model ran, this is after. So if you want to see, for example, how photolysis rate changed from the start to the end of your run, you could compare these two tables. And then it's going to show you after all these photolysis rates. Now the mixing ratios, again, this is after the model has found a converged solution. So this is, again, before and after. The first appearance of mixing ratios was the start of the model run. This is now at the end of the model run. One note here is it's also giving you this information, the total production and total loss. This is the predicted chemical production rates over the whole atmosphere of that molecule and the predicted total destruction rates chemically of that molecule. This then has some information on column depth of various molecules, as well as extinction optical depths at certain wavelengths due to certain species. That can be really important diagnostically. Then the number densities of long-lived species. This is just a different unit for the concentrations than the mixing ratios. So you can use whichever you prefer. Can make the font a little bit smaller here. This is now the fluxes of the long-lived species. Again, positive is up. So if you have a negative number here that's flowing down, positive number is up for each molecule, for each layer. This is information on species that dissolve in water, as well as the Henry's law coefficients for each species. Most of those are 0. This has some important diagnostic information. So this is the rainout rate. For the molecules, this is some information of what's happening at the lower boundary condition and the upper boundary condition. So this has the rainout rate, the rate at which things are going into the ocean in molecules per square centimeter per second. The total loss, which if I remember right, should be the sum of those top two numbers. It should be the sum of rainout rate plus feed up. the lower boundary condition type, and then the deposition velocity, which in case it's used. Okay. Then there's a space, which is followed by the total chemical production, the total chemical loss, the flux at the I think the top of the atmosphere, the flux at the bottom of the atmosphere, and then con, which is basically adding all these production and loss terms up together to see how well we've conserved that molecule. This number should be relatively small compared to the other numbers above it. A few orders of magnitude smaller than the numbers above it for every molecule. If it's not, that means things aren't well balanced. Then we have some information on conservation of sulfur, which is important for some past papers we did, and redox balance, which also, this is also an order of magnitudes thing. This is your redox balance here for any run, in particular any run where you don't have biology turned on. This number should be orders of magnitude smaller than the larger terms here to the left of it. This is also, so this next is integrated reaction rates. This is how fast each reaction in a molecule is occurring, integrated over the total height of the atmosphere. And this is a weird format, but this is the first 10 reactions. This is then reaction number 11 through 20, 21 through 30, and so on. There's 403 reactions in this model, so this ends at reaction 403. I like this because what this shows is what the fastest reactions are. You can see this reaction's occurring. These reactions here are like a 10 to the 12th molecules per square centimeter per second rate, compared to like this one here, which is only happening at 8 times 10 to the third molecules per square centimeter per second. And this is a 9 order of magnitude difference. So that's happening like a billion times faster than this one. All right, so that tells you this reaction is not nearly as important to the composition of the atmosphere as these two. And it's a good way to really quickly find out what is sort of most important to your chemistry in a given run. And you can also look at this compared to your reactions.rx file. You compare those two side by side. You can say not just what is the fastest reaction, what reaction is that? And you can also do things like say, if for all the ozone reactions that make or destroy ozone, what's the fastest ozone producing reaction? And what's the fastest ozone destruction reaction? Or you do that for any molecule. Photochemical equilibrium and inert species. So this is the number densities for the short-lived species in the model. Atmospheric parameters. This gives you some basic atmospheric parameters like the eddy diffusion constant, the number density, the pressure, the water, and some information on water saturation and relative humidity, and the total water mixing ratio, and things like that. This is the hydrogen flux, and whether or not water is condensing. Sulfate aerosol, so this is now aerosol parameters for sulfate first, then S8, and then hydrocarbons. And what this has is the aerosol number density, the radius of the particle, this is printed out for each layer, the fall velocity, the sedimentation lifetime, the eddy diffusion lifetime, the coagulation lifetime, and then a conver, which is like a conversion factor between the number of molecules in that layer and the number of particles of that species in that layer. This is then the photolysis rates printed out one more time. And that's it. And that's the end of the output file. The rest of these output files, with one exception, which I'll get to in a second, are pretty meaningless. I shouldn't say that. They're meaningful. Someone made them at some point, but they're usually specifically meaningful to some past paper or some specific output. You might dive into those if you got a specific question with regards to like the fluxes or oxygen production photo rates or like chlorine or something like that. You can also make your own output files if you're interested in something specific for your paper. But most of what you'll need most of the time is in that out.out file. Okay, so I said there's one exception, one thing you do want to pay attention to, and this is this ugly file, out.dist. So what out.dist has is the state of the atmosphere at the end of the run. It has all of the mixing ratios and all the aerosol information, as well as some temperature profile information. It has everything the code needs to have a guess at where the atmosphere is when it starts a run. So I didn't talk about this when I talked about the input files, but there is a corresponding file called in.dist, which is one layer up from the output and input files. It has the exact same structure, has the exact same molecules in the exact same order. This is basically it's like a checkpoint file. At the end of the model run, it makes out.dist. If I wanted to restart the model from the place it ended last time, I would copy out.dist one layer up and overwrite the in.dist file. And then if I go back to the place I run the code from, and I run the code again, it's going to start this run with the place I ended the last run. And you can see last time it converged in 90-something time steps. Now it converged in 35 time steps. And the reason is it was this time starting from the place it ended. And 35 is the shortest number of steps the model can take to converge. So if I did that again, it wouldn't shorten it again. And that's really, really useful because there are times you want to restart the model from the place you ended it last time. And the way you do that is, again, you just copy photochem output files. That's the folder I was in before, out.dist into photochem in.dist. And then you run the code. And then that's how you run the model. And I think that's about it. That's a pretty good overview of how to run this code, what its output files are like, input files are like, what its output files are like. If you have more detailed questions or you encounter bugs, I suggest you get in touch with us and we'll try to help you out. So that's the tutorial. I hope it's been useful to all the future people that try to use it.